Hello, welcome back. Today we're going to be taking a look at relative extrema. And we're going to do there's going to be a lot of correlation between what we covered last year in single variable calculus and how we can apply that to this year in, of course, multivariable calculus. So before we begin, let's kind of review some definitions of relative extrema. So the first definition we'll look at is what's called a relative minimum. A relative minimum says if I'm at some point that we have a relative minimum if any point around our value of our function is greater than the point where we are at. In other words, if I have a function right here, I'm at the bottom of that function if any point around this point is greater than the point where I am at. Basically says, all this says is that all points not x, y are greater than the value at x, y. Therefore, this is what we call a relative minimum. Therefore, our point is a relative minimum. Similar, we can have a relative maximum if at the point we are at, any point that is not at the point where we're at is less than where we are. So in other words, a relative maximum says, well, what if I'm up here? And I'll use AB this time. I should use AB up there. This is basically, again, saying all points not AB are now less than the value at AB. Therefore, we have what's called a relative maximum, at the point AB. Couple quick things. Again, this is very similar to what we did last year in calculus. And remember, these are also local, and that's why they call some region around AB. These are again how we find our local max-mins. To find the absolute maximum, of course, we have to use that candidates test, and we'll talk more about that in a future video. So this is very similar to our relative max-mins from last year. So how do we find these points down here? How would I find this point? How do we find where these relative maximums and minimums occur? Well, to do that, again, we have to go back to BC. In BC, we said in order to find a relative maximum, we have to find our critical numbers. We call them CN, so we'll still call them CNs in here. We have to find our critical numbers, and these are where occur from last year where the derivative was 0 or where the derivative just did not exist. And the idea is the same in multivariable. To get a critical point, or sometimes we call a stationary point in multivariable, one of the following has to be true. Notice we are saying, one, that the gradient has to be 0. All this it says right here, remember, the gradient is just a collection of all my partials. So, in other words, we have to say that all the partials derivatives have to equal 0, that all the components of my gradient have to be 0. This is saying that the partial of f with respect to x has to be 0 at our point, and the partial with respect to y at our point also has to be 0. Now the other condition is they can both be does not exist. For example, they could both be wholes. So, and that's another example right here. Now, another way to kind of look at this is kind of like saying this is like our horizontal tangent line, or in this case, horizontal tangent plane right there. So we're basically saying, like, if I'm looking at a surface right here, like let's say I have a surface, here's the agoid of mathematics. At the very top, I have if this is the top of my function, I'm looking down, my change in my x is 0, and my change in my y is 0. So that's the very top. That's going to be a critical point up here. And again, this is very similar to what we did last year in calculus. In calculus, if I wanted to find a critical number, we looked at a horizontal tangent line. Like up here, my horizontal tangent line is where my function slope would be 0. Now, when we say horizontal tangent plane, of course, this time we're basically saying our change in z is 0. That's really what we're saying here. Change in z equals 0. Remember, that gets from our gradient. So we can compare the critical points of functions from BC calculus. So let's go ahead and find our critical points for the following. So to get the critical numbers, to get the critical points, of course, we need the critical numbers. And that's, our rule just says set those partials equal to 0. So my first partial with respect to x is y. And if I set that equal to 0, we would just get y equals 0. Set my partial with respect to y, which is just going to be x. And if I set that to 0, x just equals 0. So my two critical numbers are y is 0, x is 0. Well, then how can I get my critical point? Well, my critical point just basically says now I need my z value. So I'm going to plug in my 0, 0 into my function, and that's 0 times 0, which is 0. And this is pretty boring. Our critical point is 0, 0, 0. And there's our critical point. So let's go ahead and find the critical points for the following right over here. Again, I just have to find my critical numbers first, and that's just setting my partials equal to 0. If I take the partial with respect to x, we get 3x squared minus 3y equal to 0. And if I set this equal to 0, 3x squared minus 3y, we would get y equals x squared. Find my partial with respect to y, we would get 3y squared minus 3x. And again, if I set that equal to 0, we would get x equals y squared. Now, I still don't have my critical numbers yet. They're in variable form. So I do have to solve. I do have to solve for x and y. And here's what we know. Well, if y is equal to x squared, well, I know that y is equal to x squared. I can plug that in. Then x would equal, this just becomes x to the fourth. I replace that y with x squared, then x becomes x to the fourth. And I can solve this. We would get x to the fourth minus x equals 0. And if I factor that out, we get x times x cubed minus 1 equals 0. We get x equals 1 and 0. Now, I still have to find my critical points, my CPs. My critical points, well, I have x equals 1 and I have x equals 0. I need to find y. So to get y, well, what's y going to be? Y is just x squared, so y is going to be 1. To get z, I have to plug that in, and that's going to become, let's see here. Do some math right here. This becomes 4 plus 1 minus 3, and we get 6 minus 3, which is 3. So we get the point 1, 1, 3. At 0, y would just be 0. Z would be, well, that's just 4 plus 0 minus 0, so z is just 4. So we get 0, 0, 4. And there's our answer. So these are our critical points. All right, I'm going to stop this video right here, but go to video number 2, and we're going to take a look at how we can use these points to determine if we have a relative maximum or minimum. Now, we can't use a normal sign test like we did last year in BC, but remember last year we did have the second derivative test. And we're going to talk about that in video number 2. So go ahead and go click to that, and we'll see you then. Bye.